Okay, well, that took a little bit of work, but now we're ready to investigate how the magnetization of a paramagnet depends on magnetic field. All right? I'm going to switch over to the notepad once more. So once again, we had our paramagnet. We imagine putting it into a magnetic field. When we do so, each magnetic moment acquires a magnetic energy. In our case, because J is equal to 1/2, there are only two possible orientations, either a component along the magnetic field line, spin up, or a magnetic moment with a component anti-parallel to the magnetic field, spin down. And these two states have different energies. In this case, what we found was that the magnetization should be mu b times n times hyperbolic tangent of x, where x is a factor that's equal to mu b times b divided by kt. Okay? Well, that's nice. We got a nice, simple expression. But what does this expression mean? Here we can illustrate it if we make a plot or a sketch here. So let's make a sketch here of the magnetization as a function of x. Of course, since x is proportional to magnetic field, it's really magnetization as a function of magnetic field in a way. And let me try to draw this. I'm saying try because it might be a little hard for me to do that, to get this. It might take a couple of tries. Oh, 1 second. Okay, here we go. Not so good. Let me try once more. Okay, that's a little bit better. Magnetization as a function of x, okay? And we can see kind of interesting behavior. At small fields, the magnetization is just proportional to x. Like so. This is a linear approximation. And that's because the hyperbolic tangent function is also, to a first order for a small argument, is just equal to its argument, okay? But for larger fields, we see that the magnetization saturates either in the forward direction. So this means all spins down, or in the reverse direction. All spins, oh, I did that backwards. In the forward direction, all spins up, aligned with the magnetic field. And in the reverse direction, saturation means all spins down, in alignment with the magnetic field, which now would be pointing in the opposite direction. Okay? Cool. Now, we said that in the low field limit, the magnetization is proportional to x, meaning that it's proportional to magnetic field. Let's see what that constant of proportionality means. Because magnetization proportional to field, well, that gives us a linear susceptibility at low fields. So first, let's investigate the low field limit. And what that means is that x is much, much less than 1. And then in the low field limit, tangent of x is approximately equal to x. Then the magnetization is just mu b times n, times x, which is mu b times n times mu b over kt. Or finally, m is equal to mu b squared n over kt times mu times magnetic field, which now we'll write as mu naught times h. Okay? Now we can recognize here what we found. In the low field limit, the magnetization is proportional to h. And the constant of proportionality should be the magnetic susceptibility. So we can write magnetization is equal to psi m times h, where the linear susceptibility of a paramagnet then should be equal to the following. N UB squared over KT. Let's just put a box around that. That's called the Curie susceptibility. Okay? Very good. Great. Well, that's the low field limit. What about the opposite extreme? What about the high field limit? In the high field limit, the magnetization saturates. This would be the case x much, much larger than 1. In that case, tangent of theta just goes to 1, and m becomes n times mu sub b, which is just what we expect if all the magnetic moments in the solid point in the same direction. So that makes sense too. Finally, here's an interesting question. If we think of a typical paramagnet and a typical magnetic field, is it likely to be in the low field limit, or is it likely to be in the high field limit? Which of these two answers do we need to pay the most attention to? Well, we can easily see this. Let's take a typical paramagnet, like the one that we just described. Okay, oh my gosh. And a typical field, which here we'll take to be a pretty strong field, but one that's easily attainable in the laboratory, of 1 Tesla. And we'll take the temperature to be room temperature, so that KB times T is about 0.026 electron volts. In that case, our variable x, which is mu b over KT, is going to be equal to the following. Well, you can put in the numbers, right? It's 9.27 times 10 to the minus 24 joules per Tesla times 1 Tesla divided by 0.026 electron volts times 1.6 times 10 to the minus 19, 19 joules per EV. Well, you can see immediately that this is going to be a small number. And in fact, it works out to be about 0.002. So for a typical paramagnet, even in a strong laboratory field, X is still much, much less than 1. So usually we can use the low field limit. And we find that paramagnetic materials have a linear susceptibility. Okay? Very good. And there we are. Okay? Paramagnets, then, we can expect normally to have a linear susceptibility given here, n mu sub b squared over kt, for the case where j equals 1/2. And that's what we expect. Now you can imagine, under what kind of circumstances should we get away from the low field limit? What would we have to do in order to magnetize the material so strongly that we reach saturation? Well, think about it, okay? Okay, well, let's stop here.